Welcome to Basic Electrical Engineering lecture series. This is a series of lecture videos for the first year engineering and electrical diploma students. In these videos, fundamentals of DC and AC circuits, network theorems, fundamentals of transformers, DC and AC machines, and renewable energy sources are the topics covered. Sufficient number of numericals are worked out in each session to make the concepts clear to the viewers. For a basic idea about the topics mentioned, please watch these videos from the very beginning itself. If you find the videos useful, please subscribe for the channel, like the video, and press the bell icon for notification. Please try to wear a headphone and watch the video for better sound clarity. Thank you all. And now let's start with today's session. So today's portions are magnetic circuits, Faraday's law, statically and dynamically induced EMF, and Fleming's rules. Magnetic circuits. Now here in the figure given is an electric circuit. So first let's have a comparative study between electric circuit and magnetic circuit and what are the similarities between them. So in this electric circuit there is an EMF source E. EMF source is connected to a resistance. So a current flows in the circuit I. We know the value of I is equal to E by R. Here now the magnetic circuit. So in the magnetic circuit, here in the figure given, there is an iron ring. A coil is wound on the ring which carries a current of I ampere. So in the electric circuit, there is an electromotive force. There is a resistor in the circuit. So resistance is the property by which it opposes the flow of current through the circuit. And the current flowing through the circuit is given by E by R. Now when we consider the magnetic circuit, there are analogous quantities. Now instead of electromotive force, here there is a magnetomotive force. So this magnetomotive force only is responsible for setting up a flux in the core. So magnetomotive force is equal to Ni ampere turns, or it is a product of current and the number of turns of the coil. So in the electric circuit, there is an electromotive force. In the magnetic circuit, there is an analogous quantity which is called the magnetomotive force. And this force only is the responsible for setting up of a flux in the core. And it is given by the product of the number of turns of the coil and the current through the coil. So this magnetomotive force sets up a flux in the core. And the magnitude of the flux set up in the core depends on a property of the ring which is called reluctance. Reluctance is the property of the material due to which it opposes the creation of magnetic flux in the circuit. Now in the electric circuit there is a resistance. So resistance opposes the flow of current through it, or it restricts the flow of current through it. Likewise, the iron ring has got a property called reluctance, by which it opposes the setting up of flux in the magnetic circuit. So flux set up in the magnetic circuit is equal to the ampere turns divided by reluctance of the magnetic path. Flux setup in the core is equal to magnetomotive force divided by reluctance of the magnetic path. So these are the analogous quantities. In electric circuit, I, and in magnetic circuit, phi. And in electric circuit, electromotive force. In magnetic circuit, magnetomotive force. In electric circuit, it is resistance which opposes the flow of current, and in magnetic circuit, it is reluctance which opposes the setting up of flux. Now, the next parameter is permeance. Permeance is 1 by reluctance. The reciprocal of reluctance is called permeance. Now, next is the magnetic flux density. Magnetic flux density is flux divided by cross-sectional area of the core. So here I have, here if we cut the core, then we will see a circular area, which is the cross-sectional area of the core. Assume its area is a meter square. Then the flux setup in the core divided by the cross-sectional area of the core is called the magnetic flux density. So magnetic flux density is flux setup in the core divided by its cross-sectional area. And the unit is Weber per meter square or Tesla. The next parameter is magnetic field intensity. It is nothing but the ampere turns per unit length. So the core has got a length, say L. L means the mean length of the core. So Ni is the ampere turns produced here divided by mean length of the core is called magnetizing force or magnetic field intensity. So H is equal to Ni by L, ampere turns divided by mean length of the core. So in the magnetic circuit, there is a magnetomotive force which is Ni ampere turns. So a property of the core is reluctance, which is analogous to resistance in electric circuits. And the flux setup in the core is equal to the magnetomotive force divided by reluctance of the core. Then permeance is the reciprocal of reluctance. 1 by reluctance is permeance. Then magnetic flux density, the flux setup in the core divided by cross-sectional area of the core. Then magnetic field intensity, it is the ampere turns per unit length. So the ampere turns produced here is N into I divided by mean length of the core is the magnetic field intensity or magnetizing force. Now reluctance S is equal to mmf divided by flux. mmf is equal to, we can write it as H into mean length of the core. Here H is equal to Ni by L or Ni is H into L, H into mean length of the core. Flux is equal to flux density into area. Here the equation is given flux density is flux divided by area or flux is flux density into area. So S is equal to H into mean length of the core divided by flux density into cross-sectional area. So in this equation we can rearrange as B and H, bring it to the left side. S, bring it to the right side. So it will become B by H is equal to 1 by S into length divided by area. 1 by S is 1 by reluctance, which is nothing but permeance. So you will get B by H is equal to permeance into length divided by area It's equal to permeability. So B by H, we are getting it as permeability of the core material, or permeability of the iron ring, or permeability of the magnetic medium or magnetic material. So mu is called the absolute permeability of the medium. So in this equation, for this iron ring, mu is called the absolute permeability of the media, and we can express it as the product of two quantities, which are mu naught and mu r. Mu naught is the permeability of free space and mu r is the relative permeability. So in most of the cases for this magnetic materials, only relative permeability will be given. Its absolute permeability we can find out by multiplying it with the absolute with the permeability of free space. So for example, if the relative permeability of iron is 6000, then its absolute permeability is 4 pi into 10 to the power of minus 7. That is the permeability of free space into 6000, which is the relative permeability of iron. So B is equal to mu into, B is equal to mu into H is an important relation. And also one more relation is the reluctance is equal to H into length divided by B into A. The same equation, H into length divided by B into A. B you can substitute it as mu into H. So you will get it as H and H cancels. Length divided by mu A, or L divided by mu A is the equation for reluctance. S is equal to L divided by mu A. So the important relations are B is equal to mu into H and S is equal to L divided by mu A. So flux density is equal to absolute permeability into magnetic field intensity, and reluctance is equal to length of the magnetic path divided by absolute permeability into cross-sectional area of the core or magnetic path. Then series magnetic circuit here, in addition to the iron path, there is an air gap also is there in the magnetic circuit. So in such a case, how the total reluctance can be found out? So the total reluctance is reluctance of the air gap plus reluctance of iron path. So the general equation is L divided by mu into A. For air gap, it is the length of the path is Lg divided by its permeability is mu naught. For air, the permeability is taken as the permeability of free space. Cross-sectional area same for core as well as the air gap. Cross-sectional area is the same. So this is the reluctance of the air gap plus reluctance of the iron path is Li. Li is the length of the iron path. It is marked here from this point to this point. That is the length of the iron path. Divided by mu naught, permeability of free space, into mu r, relative permeability of this iron ring, into cross-sectional area. So when the ring contains an air gap, the total reluctance is to be calculated in this way. So if there is one more material, a different material, then reluctance is to be calculated separately for each of the path. Iron path plus if this is another material, then its reluctance is to be calculated separately, and reluctance of the air gap is to be calculated separately. and add all these to get the total reluctance of the magnetic path. Now an example. An annealing of mean length 3 meter and cross-sectional area of 5 centimeter square is wound with 100 turns of wire carrying a current of 5 amperes. So this is 100 turns carrying a current of 5 ampere. Consider relative permeability as 6000. Find the flux density in the annealing, neglect leakage. So here we are assuming that the MMF produces a flux which is circulating only, which is set up only in the iron ring, and nothing is completing its path through air. Leakage is totally neglected. So now length of the iron path is 3 meter. Cross-sectional area 5 into 10 to the power of minus 4 meter square. Centimeter square is converted to meter square. Number of turns 100. Current is 5 ampere. Relative permeability 6000. So MMF is equal to Ni. 100 into 5, it's 500 ampere turns. And reluctance of the magnetic circuit L divided by mu naught mu r into A. L is 3 meter. 3 divided by mu naught is 4 pi into 10 to the power of minus 7. Mu r relative permeability 6000. Cross-sectional area 5 into 10 to the power of minus 4 meter square. We get this answer. So flux is equal to ampere turns divided by reluctance, or MMF by reluctance. MMF is 500. Reluctance, this is the value. We will get it as 0.00063 Weber divided by, to calculate flux density, flux is this quantity divided by cross-sectional area will give 1.2566 Weber per meter square. So the flux per unit area in the across the cross section of the core is 1.2566 Weber per meter square. Now another example, an iron ring has a mean length of 1 meter, cross sectional area 5 centimeter square, air gap 1 millimeter. So 500 turns of wire carrying a current of 3 ampere. Find the flux density. Relative permeability is mu r is 5500. Now length of the iron path is there, length of air gap is there, number of turns, current, relative permeability, cross-sectional area. So S is equal to iron path, we have to calculate separately. Length of the iron path divided by length of the iron path is given as 1 meter. Divided by mu naught, mu r 5500, cross-sectional area 5 centimeter square converted to meter square, 5 into 10 to the power of minus 4, plus Lg, length of the air gap 1 millimeter into 10 to the power of minus 3 meter, divided by mu naught into A. So we will get it as 1880922 ampere turns per Weber. That is the value of reluctance. Flux is MMF. MMF is number of turns 500, current is 3 amperes. So 1500 is the value of ampere turns. So 1500 divided by reluctance 0.0008 Weber. So flux divided by cross-sectional area will give the flux density, which is 1.6 Weber per meter square. Next is electromagnetic induction. So Faraday's law. So whenever the magnetic flux linking with a conductor changes, an EMF is induced in it. Whenever the magnetic flux linking with a conductor changes, an EMF is induced in it. So for the induction of EMF in a conductor, the essential condition is that there should be a relative motion between the conductor and the magnetic field. If the conductor is stationary, then the magnetic field should be moving or time varying. If magnetic field is steady, then the conductor should be moving in the magnetic field. So for example, so if the conductor is stationary and the magnetic field is varying, then it is called statically induced EMF. Statically induced EMF. Conductor is stationary, magnetic field is moving. So conductor stationary and magnetic field is moving, then it is called statically induced EMF. Wherever conductor is stationary, it is statically induced EMF. Wherever conductor is moving, it is dynamically induced EMF. Now, so assume an iron ring and a coil is wound on it, and the coil terminals are connected to an alternating voltage source. This supplies a current of I, and this current will set up a flux in the core. So since current is time varying, flux also will be time varying. Current varies in this fashion. From 0 it goes to a maximum, comes back to 0, again goes to a negative maximum, again comes back to 0. Flux also varies in the same fashion. Probably may not be in the same phase, or both may not be happening at the same time instance. But the variation of flux is from 0 exactly like this. In the same sinusoidal form, even the flux has. So the flux through the core is varying. So at a different instant, it has different values, 0 to maximum, maximum to 0, 0 to negative maximum, back to 0, like that. So what happens is that the flux, this coil, it is linking this time varying flux. So an EMF is induced in the coil. And the magnitude of the EMF is equal to, the absolute value of it is N into d phi by dt. N is the number of turns of the coil, and d phi by dt is the change of flux. N into d phi by dt is the rate of change of flux linkage. So the time varying current produces a time varying flux. Since the flux is time varying, it induces an EMF in the coil, which is equal to N into d phi by dt. D phi by dt is the rate of change of flux. N into d phi by dt is the rate of change of flux linkage. So this is the magnitude of the EMF. And its direction is given by Lenz's law. The direction of the induced EMF is such that it opposes the very cause producing it. It is opposite to the applied voltage here, and the current also. So induced EMF final equation is minus N into d phi by dt. The induced EMF in this coil opposes the very cause which is producing it. So the EMF induced in this coil is given by minus N into d phi by dt. This is an example of statically induced EMF. So in this case, the coil is stationary and the magnetic field is time varying. Now let's see the magnetic field produced by a current carrying conductor. So the current carrying conductor, suppose a conductor is carrying a current I, a magnetic field is produced around it. So the magnetic field is in a plane perpendicular to the conductor or perpendicular to the current. So the direction of the magnetic field can be obtained like this. That is, you hold the conductor in your right hand with thumb in the direction of current, then fingers encircling the wire will give the direction of magnetic field. That means hold the current carrying conductor in your right hand with thumb indicating the direction of current. Then fingers encircling the wire will give the direction of magnetic field. So if you hold this conductor in your right hand, then see the fingers. Fingers will give the direction of the magnetic field. It is like this. So this is the magnetic field produced by a single current carrying conductor. And what about the magnetic field produced by a coil? See figure 1. Consider figure 1. A current, this one entering a coil. A current is entering it. So here I'll mark the current direction with a cross. That means current is going in. And from this side it is coming out. Again here it is going in. Here it is coming out. So when current going in, I put a cross mark. Current coming out, put a dot. So this point 1, this is 1 dash, here a 1, this is 1 dash. The next conductor also it's the same. So what is the uh, field produced? What is the direction of the field produced by this current? So you keep your uh, thumb nail on this cross mark and see what is the direction. So you can see it like this. Keep your thumbnail on this cross mark and see what is the direction of the magnetic field. You will get it like this. So this conductor also will produce same. And what about this current? Point the thumb towards your face and see the direction of the fingers. Here also this conductor also point the thumb towards your face and see the direction of fingers. So this is the direction of the magnetic field. Or there is another way to find it out. Just hold the coil with fingers in the direction of current. That means you have to hold the coil with the fingers in this direction and see the direction of thumb. Thumb will be like this. So that is the direction of the magnetic field. That way also you can find out. Now if the current is reversed, so this is current is entering it. Here current is leaving the coil. So current direction is reversed. So already this side it is current is coming out. Here current is entering. So see the mark the direction of the field produced by it on this dot. You keep the point the thumb towards your face and see the direction of fingers. And here put the thumbnail on this cross mark and see the direction of fingers and mark the direction of the field. You will get it like this. Third case, so this is first and second, current direction reversed. Here current in the same direction, winding sense is reversed. Here in the figure 1, it is say it is found in a clockwise sense, we can say. Here it is in the opposite sense, counterclockwise sense. So this side conductors current coming out, here current entering. So it is like this. Again the magnetic field, it is similar to this. So this will set up a field like this. So what is the difference between figures 1 and 2? 1 and 2 is current direction is reversed. So the direction of the magnetic field also is reversed. What is the difference between this is figure 2, this is figure 3. What is the difference between 1 and 3? 1 and 3 current is in the same direction but winding sense is reversed. Winding sense is opposite now. So through the coil current flows in the opposite direction. Okay. Externally current entering in the same direction but the winding is in the opposite sense. So again field is reversed. So next is dynamically induced EMF, where the conductor is moving. Now assume a singleton coil rotating in a magnetic field. You will be familiar with this example, and you may be familiar with the EMF equation also. So one equation is EMF induced in a singleton coil is B into A omega sin omega t, and another equation is 2 BLV sin theta volts. Both are same from one, we can derive the other one. Here in this equation, B A omega sin omega t, A is the loop area. This is A meter square. And omega is the angular velocity. So the coil is rotating, whatever is the angular velocity of the coil, rotating coil, that is represented by this omega. This is the sine omega t. Omega is the angular velocity, t is the time, so this is the angular displacement theta. Omega t is same as theta. So substitute for omega with v by r. The relation between angular and linear velocity. Linear velocity is equal to angular velocity into radius. This is, take this as the radius, because this is the axis of rotation. So here, this is the axis about which the coil is rotating. So V is equal to omega into R, and area of the loop is, this is, take this as length of the conductor, and this is radius. So area of the loop is L into this length. This length is R plus R, 2R. So substitute it, instead of in place of A, put L into 2R, and in place of omega, you put V by R. You will get E is equal to 2 BLV sin theta volts. So this is the EMF induced in a singleton coil. Now see in this figure, the coil, the plane of the coil is vertical. So plane of the coil is vertical. That means, say this conductor, this conductor is A, this conductor is B. So conductor A is here, B is here. So the plane of the coil is vertical. Now assuming this rotating in clockwise direction. Now at this point, the flux density is downward. So the flux is directed from north to south. Flux density is downward. Towards right is the velocity vector. This is linear velocity. So this is the direction of B is the direction of flux, and V is the linear velocity at this point. So EMF induced is equal to in this conductor is B in one single conductor is BLV sin theta, where theta is the angle between B and V. Theta is the angle between flux density and linear velocity. Now in the vertical positions, now here the conductor is moving, always the conductor moves tangential to the circle. Circle means the circular path. This is the path of rotation. So always the linear velocity vector will be tangential to this circular path, and flux density vector is downwards. So this is the first figure. Here the linear velocity vector is downward, flux density vector is towards right, and flux density is downward. So theta is equal to 90 degree now. Now assume the plane of the coil is horizontal. That is means from this position after a 90-degree rotation, the plane of a coil will be horizontal. Now this is coil A, coil side A, this is coil side B, or conductor A, conductor B. This is A, B is rotating in clockwise direction, and after 90-degree rotation, it is in this position. Now the velocity vector, linear velocity vector is downward, flux density vector is also down, so theta is equal to 0 degrees. So at this position, the induced EMF is 0 when the plane of the coil is horizontal. When the plane of the coil is vertical, theta is 90 degree and the induced EMF is maximum. Now take an intermediate position. This is the velocity vector, which is always tangential to the circular path. This is flux density vector, which is always down. So this is theta. This angle is same as this. So at this point, though theta has got a value between 0 and 90. Here in this case, theta is between 0 and 90. Here it is when it is vertical, theta is 90 degree. When it is horizontal, theta is 0 degree. When it is at an intermediate position, theta is between 0 and 90. So this is an example of dynamically induced EMF. Dynamically induced EMF, the conductor is moving and the field is steady. The field is not time varying. In a steady field, a conductor is moving. So induced EMF in the coil is here the coil has got two conductors A and B. So the EMF induced in A and B will get added because it will have opposite direction. If it is like this, EMF is in conductor A is like this, then in B it will be in the opposite direction. So at these terminals you will get the sum of these two EMFs. So EMF induced in the coil is equal to 2 BLV sin theta volts. So in this case, the direction of EMF induced can be found out by Fleming's rules. So Fleming's right-hand rule is meant for to find out the direction of induced EMF in a generator. Now the rule is like this: hold the forefinger and middle finger of the right hand in three mutually perpendicular directions. When thumb indicates the velocity vector, forefinger indicates the flux density vector, then middle finger will indicate the direction of induced EMF. So your right hand rule is always used for finding out the direction of induced EMF. Say here, in this case, what is the direction of induced EMF? Let us find using Fleming's right hand rule. So hold your right hand with the forefinger in the direction of flux density and the thumb in the direction of velocity. Then middle finger will indicate the direction of induced EMF. If you hold your right hand in three mutually perpendicular direction with forefinger in the direction of flux density, thumb in the direction of linear velocity, then I'll put a cross mark here. Then the your middle finger will be inward. That means the induced EMF must go to this direction in conductor A. And obviously in conductor B, it will have opposite direction because the direction of velocity vector is reversed. So this conductor, it will have opposite direction. And at the terminals, you will get the sum of these two voltages. So hold your right hand in the case to find out the direction of EMF induced in conductor A. Hold your right hand with thumb in the direction of linear velocity vector and forefinger in the direction of flux density. then your middle finger will give the direction of the induced EMF. So on this figure, if you keep your right hand with the three fingers in three mutually perpendicular directions, then your middle finger will be inward into the paper. That means this is the direction of induced EMF. On B, you will get an opposite direction. So that is Fleming's left hand rule. So these three quantities are in three mutually perpendicular. This is 90 degree, this is 90 degree, this is also 90 degree. So you can consider this as the edge of a cube. Edge of a cube. So you can mark the three parameters there. Velocity, flux density, and induced EMF. The last is Fleming's left-hand rule, which is meant to find out the direction of force experienced by a current-carrying conductor in a magnetic field. So this rule gives the direction of force experienced by a current-carrying conductor. Now the rule is hold the thumb, forefinger, and middle finger of the left hand in three mutually perpendicular directions. This time it is left hand. So forefinger in the direction of flux density, middle finger in the direction of current, then see what is the direction of thumb. That will be the direction of force experienced by this conductor. So when a current carrying conductor is kept in a magnetic field, it experiences a force, and this rule, Fleming's left hand rule, is used to find out the direction of the force. So the three fingers of the left hand keep in three mutually perpendicular direction, with the forefinger in the direction of flux density and middle finger in the direction of current. In this case, middle finger is inward and your forefinger is downward. Then you check the direction of the thumb. That will give the direction of the force experienced by the conductor. Okay, that's all for today's session. I hope you like the video. Please subscribe for this channel. And if you like the video, please share it among your friends. And also press the bell icon for notifications. Thank you.